Everyone, welcome to iSmile Camping. Today we will study about K-maps. So what are K-maps? So a K-map is a diagram used to simplify Boolean expressions. It helps reduce logic functions to their simplest form. So if we have a logic expression, and if we implement that, maybe we may require large number of gates, but by using K-map we can reduce the Boolean expression so that the number of gates required are less. So the main purpose is to minimize the number of logic gates for the required digital circuits, making them more efficient. Now, what about the various types of Boolean expressions? So we can convert any Boolean expressions to two types. The first is sum of products expression. So this is an example of a sum of product expression. So here we have this are the individual products, this one product, the another one, the third one, and we are summing them. So this expression is called as a sum of product expression. Then we also have another type of Boolean expression called as product of sums. So here, as we can see, there are two sums and we are getting the product of this. So this type of expression is called as a product of sums. So why do we need to convert the expression to this sum or SOP or POS form? Now in case of SOP expression, when we want to design the circuit, we take the mean terms which are denoted by small m, for which the output is 1, and we use NAND logic or AND OR logic to realize the digital circuit. And for POS expression, we take the max terms which are denoted by capital M, for which the output is 0, and for implementing this we need NOR or AND logic. Now what are max terms and mean terms? So suppose if we have a two variable truth table, so here I am not showing the output, what output we want, what output we should get, but I want to show what are max terms and what are mean terms. Let us see what are mean terms, how we write the mean terms from the truth table. So this is a two variable truth table. So we have four combinations 0 0 0 1 1 0 1 1. So the first mean term here, a bar dot b bar. So when a is 0 we write a bar, when b is 0 we write b bar, and a bar dot b bar. In the second term, a bar, so a is 0, so we have a bar, b is 1, so we have b. In the third row we have a as 1, b as 0, so a dot b bar, and finally we have a and b as 1, so we have a dot b. And this max term is totally opposite of this. So if in mean term we have a bar, this becomes a, dot becomes plus, and here b bar becomes b. So this is almost opposite of this. Now how do we construct a K-map? So suppose we'll first see how we can have a three variable K-map. For that purpose we need a truth table. So this is a truth table, a three variable truth table. So we have a, b, c as the inputs, and with three inputs we can make 8 combinations 0 0 0 0 0 1 0 1 0 up to 1 1 1. And I am just selecting this, I am just getting this output. So we can take any random output for our study purpose. So we consider the K-map as follows. So whenever we want to draw the K-map, for example, we see first the SOP K-map. So in SOP K-map we need to draw this K-map. So all the three variables are here, and this is how we need to write. So first a bar dot b bar, then a bar dot b, then a dot b, and a dot b bar. We have to strictly follow this sequence. So because when we are going from this a bar dot b bar to this a bar dot b, only b is changing, and from a bar dot b to a dot b we see a is changing, and from here to here when we go from a dot b to a dot b bar, as we can see only b is changing, and when we come from this a dot b bar to a bar dot b bar, a is changing, and here we have c bar dot c. So this is first we draw this map, and then now we populate this K-map with the output. Okay, so see how we write the first input. We have to actually write this output into the this K-map inside this. So first is a bar, so first is a, b, c, and at a we have 0, at b we have 0, and at c we have 0. So a 0 means a bar, b 0 means b bar, c 0 means c bar. So here this output 0 of y will come here. Okay, this is how we populate. Now next input is a is 0, b is 0, and c is 1. So it is a bar, b bar, and c, and this output y will be inserted here. Similarly, in the third case we have A0, B1 and C0. So it is A bar, B, C bar. So this A bar, B and this C bar, and this 0 will come here. And the fourth one, is A B C as 0 1 1. So it is A bar B C. So it is A bar B and C is here, and this 0 will come here. Similarly, we write all the other outputs. So this is how we draw the SOP K map for a 3 variable truth table. Now how to implement the POS? Now see the change. We have the POS K map. Everything inside whatever is there inside the this box is same here inside POS. Only the things are here we have, this is the, as we can see, these are the mean terms and this is the max terms. Okay, that is what the change is. This is same, as you can see everything is same. The changes are here. A bar dot B bar becomes A or B, then A bar dot B becomes A or B bar or plus, then this A dot B becomes A bar plus B bar, and this A dot B bar becomes A bar dot B, and this C bar becomes C and C becomes C bar. This is how we draw the SOP and POS K map. Okay. Now let us see how we can construct a 4 variable K map. First of all, SOP. So we have this truth table. So there are 4 variables A, B, C, D. So with 4 variables we have 16 combinations. Okay, and this is, I'm just taking this output randomly because I'm just taking 8 zeros and it was randomly. So this is how we draw the K map. Okay, so here in the previous case, as we saw, A bar dot B bar, A bar dot B, A B, and A dot B bar, and here because we have two terms, so here C bar dot D bar, C bar dot D, C D, and C dot D bar. So whatever we are going this way, we are going this way. Okay, and this is what we get. Okay, so this 0 comes from A bar dot B bar dot C bar dot D bar. Okay, and this comes from here. Okay, so we populate this. Okay, you can check this. I've done this. Okay, so we are making the entries from this truth table into the K map. Okay, so this is all the arrows are pointing. You can slow it down and check it yourself. So this is how you draw the K map. Now with respect to function also we can that was the SOP K map. Now we can actually express this entire truth table by a single line function. So now what I am going to show is how we can represent the truth table by a single line. Okay, so this is the truth table. So there are 16 entries here, 16 rows. So it will become difficult again and again to just write the entire truth table. So we can actually write a short form notation of this truth table into a function. So how do we write? The first thing what we do is we insert the cell numbers. Okay, so as you can see, this I have inserted one column as cell numbers, and these are the cell numbers. So I start from 0, 1, 2, 3 up to 15. Okay, so the input 0, 0, 0, 0, it represents 0. Of course, you can even say that this is the decimal of all zeros. Then 0, 0, 0, 1 is 1, 0, 0, 1, 0 is 2, 0, 0, 1, 0 is 3. So instead of writing this, we write this into a decimal form. And then how do we write? So this is the cell. These are the cell numbers we are getting. Okay. Now this is the SOP representation of this entire truth table in one single line. Okay, so this represents the SOP. This is the SOP representation. We can also have POS representation, but let us see what is the SOP representation is. So it's F of ABCD, then sigma small m. So as we know in SOP we have the mean terms for which output is 1. So this is what we are having. Now see, the cell number 1 has the output as 1, so therefore this 1 is written here. Then the next one, as we can see, it comes at cell number 4, so this 4 is written here. Then the next cell number which is 1 is 6, so 6 is written here. The next cell number which is 1 is 8, so we write this 8 here. Similarly the next is 9, so 9 comes here. Then we have 11 which comes here. Then we have 13, it is written here. Then finally we have 15 which is written here. Okay, so in short, whatever these cell numbers, they are all 1 and rest are the zeros. So because it's the mean term. Now we can also have the POS representation. So as you can see, this is F of ABCD equal to this. Now sigma becomes capital Pi and small becomes capital M, and all these cell numbers, they are actually output is 0. Okay, so here we have this. Okay, 0, then 2, then 3, 5, 7, 10, 12, 14. This all are actually you can say zeros. Okay, now this is the cell representation as we have seen. Okay, now suppose if we are given the function, then how to draw the K map where the cell numbers lies inside the K map. So this is 0, the place where the 0 cell number will be there. This is 1, So 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So this is what we have the cell numbers. So if we are given the function, we can use this cell numbers to insert the entries for zeros and ones. So if we are not given the truth table, we can use and we are given the function, we can use this particular representation to insert the zeros and ones. Okay. And even for POS, the cell numbers are same. Only the changes is this the A bar B bar becomes A or B, A bar dot B becomes A bar, A and B bar, and so on, A or B bar, and so on. So this is the cell numbers remain the same. Okay. Now let us see the representation. Okay. Now suppose we have a SOP function. Okay, we have this SOP function and we are given this sigma small m 1 4 6, and we have to draw the K map. So this is the K map. So this is the K map. Okay. So here this is the SOP, sorry. This is the SOP and this is the POS K map. Okay, all these cell numbers 1 4 6 8, if we go back and check, this all are 1 and rest all are zeros. In the POS, if we have this pi and capital M, then all these cell numbers will become 0 and rest will become 1. Now before solving the K map, we must know what are pairs. Okay. So in K map, it is a group of two ones when we have SOP, or two zeros in POS which are horizontally or vertically adjacent. So whenever we get that, we encircle the pair and eliminate the variable that changes form. So suppose this is the K map, one is the left side is the SOP, right we have the POS. So here we can see there are two ones which are horizontally adjacent and two ones vertically adjacent. So and here on the right side we have two zeros horizontally adjacent and two zeros vertically adjacent. Now how do we write the equation for this pair, both the cases? So this is the equation of the pair. So this is the equation of the first pair, B dot C bar dot D bar. So in this particular pair we see B and C bar D bar, they are not changing, A is changing. So A bar becomes A and rest all the same. So whatever changing, we eliminate that. Now in the second pair, what is changing is, as we can see vertically, we see this C bar and C. So C is changing. So what is common is A bar dot B and this is D. So this is the equation of the pair. Then on the right side we have this D is changing in this case. So we only have A or A plus B plus C. In the second pair, what is changing, as we see B is changing. So we eliminate B and write the remaining terms. So this is the pair. Now quads. So quad is a group of four ones in SOP or four zeros in POS K map which are horizontally, vertically adjacent or forming a square. So when we have a quad, we encircle the quad and eliminate the variables which are changing the form. So here we have two K maps. On the left side we have SOP, on the right side we have POS. So here this four ones, they are making a quad, and this circle they are forming again two quads are there. On the right side we again have a quad of four zeros and four zeros vertically forming a quad. Now we write the equation of this quad as C bar dot D bar, because in this, from when we go from this one to this one, A and B are changing. So we eliminate A and B, only the constant terms we write this C bar dot D bar. In this particular quad, what is changing is B and D are changing. So we eliminate B and D. So in this entire circle, when we move on this, all the ones, we see B and D are changing. So we write the things which are not changing. On the right side, we have this A bar AA plus B, because C and D are changing. Okay, and in the next one, what we see is B and C are changing. So we have A bar plus D bar. Next is octets. So octet is a group of 8 ones in SOP or 8 zeros POS which are horizontally or vertically adjacent. We encircle them and eliminate the variables that change forms. So here we have, in case of SOP we have 8 ones, and also in case of POS we have 8 ones. We encircle them, 8 zeros actually. Okay, so in this entire octet, only C bar remains constant. So it's entire all ones, A, B and D are changing. So we just have C bar. On the right side, A is not changing, rest all are changing. So we eliminate all the others and only A remains. So when we are solving a K map, we first find the octets, okay, then the quad and the pair. So a pair eliminates only one variable, quad eliminates two variables, and octet always eliminates three variables. So after constructing the K map, first we find the octet. If we are not getting, then we find the quad. Even if there is no quad, we find the pairs. Okay, so this is the sequence. Now before solving the K map, we must know the properties of K map. The first is ruling the map, eliminating the redundant group, considering a term more than once, and dealing with the don't care conditions. So let us see what is the meaning of ruling the map. Now consider this K map. In this K map, what we observe that this of course a SOP K map. This property is also same for POS. So in this K map, we have two pairs. Now we write the equation of the two pairs as this one, a bar dot b bar dot c bar plus a dot b bar dot c bar. So these are the two pairs. Now we can use the property of K map by which we can roll the K map so that instead of getting two pairs, we get a quad. So as you can see the green portion, so if we combine these two green portions and that is rolling the map, then we are getting a quad instead of two pairs. So the equation becomes more efficient. So only we have b bar dot c bar instead of the previous one. So we can roll a K map in this way. Then how to deal with isolated term? Now in this K map, when we observe, we get a quad and this is the isolated term. Now we can use a K map by which we can actually so this is the actual equation of a K map. Okay, then suppose if we use this particular this upper one so that we can form a pair. So this isolated term can whenever we are getting an isolated term, we can see around and see that we can actually form either a pair or a quad. So the equation reduces. As you can see, the equation gets reduced. So we can use this one more than once actually. Okay, then we have a redundant group. Okay, now what is the meaning of a redundant group? So in this K map, what we observe is we have three pairs. Okay, now the equation of K map with this three pair is this one. Okay, but this the one group as the pair, as we can see, it is completely encircled in the other groups. Okay, that two ones, they are completely coming are covered in the other pairs. So this pair is called as a redundant pair. Okay, or a redundant group. So while writing the equation of K map, we eliminate this. So we don't need to write this equation, we just write to the equation for the two pairs. Rather than that, so we can eliminate that particular thing. So the equation reduces. Then finally, how to deal with don't care. Now what are don't care? So in many situations, we don't care what output we are getting for a particular input condition. Such conditions, they are called as don't care conditions. Okay, so they are denoted by X. So for this particular input, whether we are getting 0 or whether we are getting 1, we don't care. Okay, so these conditions can be considered as a 0 or 1 based on how much benefit we can get. Okay, so suppose this is the K map we are getting from a truth table. Okay, and in this K map there are three don't cares. Okay, now if we construct the K map, maybe like we will have this forms a pair and this form, so we only have two pairs, but we can use this particular don't care so that we can consider this don't care as 1 so that we get a quad. Okay, and we left this don't care as they are, we don't take them into consideration. So these are not useful, these two don't cares are not useful for us, but this is useful because if we consider it as 1, then we get a quad. Okay, so don't cares can be used as if they are beneficial to us, we can consider them as 1, and if they are not, we can leave them as they are. So we get equation as y equal to c bar dot d. Okay, so this all the properties of K maps. So that's all for this session. Now you can go and solve some K map problems. Thanks for watching.